Hello, in this video we're going to learn how to use the matrix inverse to solve for a linear system of equations. In the previous video we learned how to transform a set of simultaneous equations to a matrix representation of that format, AX equal to C. Now the question is how to solve for X. Maybe when we look at this equation, it looks like a very straightforward algebraic equation, and we can say, okay, like let's divide both sides by a so that I have a solution for x equal to c over a. While algebraically it looks sound, this is not right matrix operation. There is no operation called a matrix division, and instead we have to use what we call a matrix inverse. Okay, so if you consider the matrix inverse exists for square matrices. So if it exists, we're gonna denote the inverse as a super minus 1, such that when you multiply the matrix by its inverse, we're gonna get the identity matrix. So as a result, we can prove that the solution for our unknown vector x is equal to a inverse times c. Let's see the step-by-step solution for that. So after we transformed our linear system of equation into the matrix format, this is the equations that we have. We wish to solve for x, so we wish to have x on one side and everything else on the other side. So one way to do so is to multiply this equation from the left by a inverse. So here we multiplied by a inverse from the left. A inverse times A would give us identity matrix, and on the right hand side we still have A inverse times C. Identity matrix times any vector or any other matrix will give this matrix again, so I times x will give us x, so we have x alone on the left hand side, and the right hand side is now A inverse times C. So now simply, if we have a linear system of equation, you write it into this matrix format, your solution would be simply you take the inverse of the coefficient matrix, multiply it by the right hand side vector, and you have your solution. This is very straightforward, very simple, and doesn't require a lot of steps compared to the previous methods that we covered in an earlier video. So now let's talk more about the properties of a matrix inverse. So by definition, matrix inverse only exists for a squared matrix. So this means that if we would like to use matrix inverse to solve for unknown parameters, we should have a number of equations equal to the number of unknowns so that we can take the inverse of A. Then, if I have a matrix A and I find another matrix B such that when you multiply A times B you get identity, then you can immediately say that B is the inverse of A. And if A has an inverse, then we call that A is invertible, or in other words, non-singular. Okay? So we say that a matrix is invertible or non-singular if its inverse exists. On the other hand, not every square matrix has an inverse. So if you have a matrix that doesn't have an inverse, we call this matrix as non-invertible or singular. So if I have two matrices that are square matrices and you multiply them together, give you identity, this means that B is the inverse of A, and also A is the inverse of B, and both are invertible. And when you multiply them together, you're gonna have identity. An invertible matrix is called non-singular. A non-singular matrix or an invertible matrix has these two properties. All rows and columns are linearly independent, meaning that I cannot get one row as a linear combination of the other rows, and same for the columns. I cannot get one column as a linear summation or linear combination of other columns. If this happens, this means that this matrix is non-singular and its inverse exists. So let's see this example. We would like to determine whether this matrix B is the inverse of A. Okay, so one way to do so, let's multiply B times A. If B is equal to A inverse, then this multiplication should correspond to A inverse times A, and the result should be the identity. If B doesn't equal to A inverse, this result here wouldn't equal to the identity. So let's verify by doing the multiplication. We don't need to manually compute it. So let's multiply A times B or B times A. Both would be the same. So I have B 3, 2, 5, 3 times A negative 3, 2, 5, negative 3. So I have 2 by 2 matrix times a 2 by 2 matrix. The result would be a 2 by 2. So I start by first row, first column. So I have negative 9 plus 10. How about the first row, second column? So you're gonna have 6 minus 6. We do second row, first column. So we have minus 15 plus 15. And finally, we do the second row, second column. So we have 5 times 2 give us 10, plus the multiplication of 3 times negative 3 give us minus 9. So when we do that, we're gonna have 1, 0, 0, 1, which is the identity matrix. So if I have two matrices, multiply them together, I get the identity. This means that one is the inverse of the other. So here, yes, P as the inverse of A. Now let's move to the computation of the inverse matrix. In this course, we're going to focus on a 2 by 2 matrix. And if we have a larger matrix, we're going to use either MATLAB or calculator to solve for the inverse. Okay, so let's analytically focus on a 2 by 2. So assume that I have a 2 by 2 matrix whose elements are A, B, C, D. To get the inverse of the matrix, we're going to divide by the determinant of that matrix. The determinant of a 2 by 2 matrix would be simply the multiplication of the diagonal elements minus the multiplication of the diagonal elements. So it would be AD minus BC. And then I'm going to swap the diagonal elements. So here I have A and D. I swap them together and then change the sign of the off-diagonal elements. Okay? So let's do this example together. I have this matrix A and I'd like to compute its inverse. So to compute A inverse, we're going to divide by the determinant. So the determinant here would be the multiplication of the diagonal elements. So minus 3 times minus 3 gives us 9, minus the multiplication of the off-diagonal elements, which give us 10. And then we're going to have a matrix. We swap the diagonal elements. So I have minus 3 and minus 3, and then change the sign of the off-diagonal elements. So it's minus 2 and minus 5. Okay, so this term here gives us negative 1. So we have 1 over negative 1 times minus 3, minus 2, minus 5, and minus 3. Complete multiply this by this negative 1, we're going to end up having 3, 2, 5, and 3. So this is what make A inverse. So far we have learned how to solve for the linear system of equations. So if I have linear system of equation, we can write it into a matrix format like that. And then we learned how to use the inverse to get solution for x. So x would be A inverse times C. And we learned how to get the inverse for a 2 by 2 matrix. So let's wrap this together and have a big example in which we solve simultaneous set of equation using the matrix method. Okay, so let's assume that we have these two equations for two unknowns. So I have two equations and two unknowns, x and y. And again, those unknowns might be the current and voltage in your circuit that you'd like to solve for. Okay, And we'd like to solve for those x and y using the matrix method. So step number 1 would be put the two equations into the matrix format. So put our equations into the matrix format. This would be a very straightforward process. We're going to have a coefficient matrix. We're going to have a matrix of our variables x and y. And on the right hand side, we're going to have the result. Okay? And by the way, the order of the equation doesn't matter. So this could be equation 1 and this equation 2. So you fill in the rows. Row number 1 corresponds to equation number 1. So it's 2 and 1. So coefficient of x is 2. Coefficient of y is 1. And then you move to the second equation. Coefficient of x is 1. Coefficient of y is -1. And then the result for equation 1 is 4. And for equation 2 is -1. So this is the matrix format. Okay? If you decided to start by equation 2 first, you're going to end up having a different matrix format, but the end result would be the same. So let's assume that I'd like to have a matrix format where I'd like to start with equation number 2 first. So I have my two parameters, x and y. Okay? So if you start by equation 2, the coefficient of x is 1, the coefficient of y is -1. Okay? And before you forget, you write down the corresponding answer, which is -1. Okay? Then you can fill in the second equation. This coefficient is 2, coefficient of y is 1, and the result is 4. Okay? So this also is an acceptable format. And if you do the matrix inverse here and or here, you're going to get the same exact result for x and y. Okay? So let's stick with this first format on the left. So we have our matrix format 2, 1, 1 and -1 times x and y, and that was equal to 4 and -1. So this is a x equals to c. So where x, vector x, is the vectors that contain our unknowns x and y. So we can solve for x as a inverse times c. So step number 2 here is now to get the inverse of a. Find a inverse. Okay, so a here is a 2 by 2 matrix. So we're gonna divide by the determinant. It's 1. The determinant as the multiplication of the diagonal terms minus the multiplication of the off diagonal terms, and then we swap the diagonal terms and change the sign of those off diagonal terms. So here I have 1/3. So a inverse would be simply 1/3, 1/3, 1/3, and -2/3. Okay, once I have that, we use this equation to solve for our unknowns. So we are ready for step number 3, which is generating that solution. So number 3, x is equal to a inverse times c. So we have an expression for a inverse. It's 1/3, 1/3, 1/3, minus 2/3, and here we have c equals to 4 and -1. When we do this multiplication, we have the following. We have 1, and here we have 2. So this is the solution for our parameters x, and remember that this x was the vectors that contain our unknowns x and y. So from here we say that x is equal to 1 and y is equal to 2, which is the same solutions that we obtain using the other methods, but now this doesn't require a lot of steps. Once you put your problem into the matrix format, you take the inverse multiplied by the results column and give you the final solution.
Thank you.